Alright, let's continue on to the next stage of learning about processors, and the next part comes with pipelining. And pipelining should be at least somewhat intuitive, a way in order to improve performance. So if you recall from previous processors, the main issue is that the longest running instruction slowed down the rest of the processor. And so we came up with a multi-cycle solution for this, but there's another way to go about at least relieving this issue of variable length instruction execution. And one way to do this is with pipelining. And pipelining should be intuitive because hopefully you all do this when you do your laundry, for example. When you do your laundry, what you don't do is put it in the washing machine, take it out, put it in the dryer, take it out, fold it, put it away, and then start your next load. What most of y'all do is pipeline it such that once you take it out of the washing machine, you put it in the dryer, you take the next load and put it in the washing machine. Therefore, you're overlapping the different loads or the work on the different loads, because while one is drying, the other is washing. And of course, hopefully, if you do fold your clothes, because I know probably most guys don't. Anyways, but let's just assume you do. So when you do go to fold your clothes afterwards, you have another load in the dryer and another load washing. Well, pipelining is the same idea. You're just going to break up the instructions and do different parts of the instructions in order to overlap. Alright, so before we go on to that, let's talk a little bit more about performance metrics, because it is important to realize what it is that pipelining is improving. First off, there's the response time of aka when my job is done, i.e. when I give you a job, how long does it take to come back? Will my books arrive from Amazon? When will and how long will this program or instruction take? Are two examples of response time. You start off something, when is it going to come back? Throughput is how much work can be done in a specific time, and this is not the same thing. How many books will Amazon sell this week? Well, all the books may have the same response time, but if Amazon ramps up the number of warehouses and whatnot, then it can sell numerous books with the same response time, and therefore its throughput is much higher because it's able to send through more data. Another example I like to think of is when you're on a road, your response time is the speed limit, because that's how long you should take to go from point A to point B. Your throughput is basically how much cargo can you carry. If you're on a small car, you can't carry that much, but if you're on an 18-wheeler, then you can carry a lot more and your throughput is higher. We'll just say for the sake of argument the speed limit's the same on both, so they both have the same response time, but the 18-wheeler would have more throughput because it's able to carry more. And so the idea here is when we go to programs is how long does it take, response time is how long does my instruction take to complete, and throughput is how many instructions can I complete per hour or per second. Improved relatively easy by multiprocessors, but we're again still focusing on single processor design. For those of you continuing on operating systems, you'll quickly discover how treacherous multi-threaded programming is. So we're going to stick with single-threaded for now. Alright, so the performance that we like to stick to is clock cycles per instructions, namely how many clock cycles does it take. In our single cycle design, it was always 1 because every instruction took 1 cycle. Multi-cycle increased it, but then CPI back with pipelining is going to change things up a bit. But let's go ahead and look at it. For a multi-cycle processor, we use cycles needed for each instruction, mix of instructions, and so we'd sum it up and then basically divide it out was the average number of clock cycles per instruction for an application. Single cycle is 1, multi-cycle is greater than 1. Next step, improve CPI. We want to make lower and better. The easiest thing to do is work on multiple instructions at the same time, which is what our pipeline is going to do, i.e. while your clothes are in the dryer, you also have clothes in the washing machine. So you're going to have work on multiple instructions at the same time. Alright, so it is a good idea to at least go through some idea of, or at least some history here. Want to execute instruction in 1980s, you usually built a processor, multi-cycle, find some instructions, line them up, and then possibly overlap the execution, fetch 1, fetch 2, send them in the ALU. This was called a pipelining instruction set. It was used first extensively in the 1960s, but it really didn't come into its element until 80s/early 90s. The idea here is CPI approaches 1 because while each instruction may take multiple cycles to complete, since you're overlapping so many instructions, on average, your CPI will eventually become 1. Alright, and we'll talk about why this is advantageous over a single cycle design in a bit, but mainly it's because since you're chopping up the instruction, that means that each stage of the pipeline, or each piece of the pipeline, is going to take a smaller amount of gate delays to complete, which means you can improve your clock cycle and therefore overall have a higher throughput of instructions. Alright, so here's our recap of our LC64 design. I've realized just looking at this that some of these numbers are a little off, but we'll move on for now. Multi-cycle design looks something like this. Big takeaways here is we got rid of our extra adders, but we added a whole bunch of control logic. And so these slides like to go through a working analogy with whitewater rafting. The author loved whitewater rafting, so we'll go ahead and stick with it. Or kayaking, depending on what you prefer. So the timeline is about the same as multiprocessor, you notice, which is kind of amusing. In the 70s, only a few things were happening on the fringe. 80s, new adventure, and by 1990s, which I'm sure you all find and hold very dear to your heart, it was a business. So in the 50s, you want to go rafting, you find some old Army surplus raft, you find a river, you throw it in, you float to the end, you get out. Yeah, that's basically what it was in the 70s. So the number of people in the river, 1, and usually you had 1 person in the river until dawn because there weren't that many people doing this. So you build it in processor, find instruction, put instruction in processor, run instruction, get out. This was a single cycle data path in the 70s. Multi-cycle river. Ooh, these are always fun little pictures because, for example, which way is the water flowing? Anyways, rafting in the 80s, find a new rafting company because people were getting into it. Pay your fee, line up the rafts, float, get out, clean up. Guides possibly cleans up, so you can probably hold about 20 or 30 people, maybe 100 people in a river a day. This was the multi-cycle one, find instruction, line them up, and this was the pipeline instruction. Luckily, the average CPI can get down to 1 if you line up all these instructions correctly. Rafting in the 90s, a little more of a find one of 20 plus rafting companies because now it's a pretty big business. Pay your fee and float calmly in line just like a freeway, get out, make guides clean up everything because who wants to do all that work? And usually you can have a lot more people on that river. Lots of people on the river all day. Although right now, there's probably not too many people out there. So processor in the 90s, execute as many instructions at the same time. You might have 12 to 20 cycles of forward instruction. Notice that in our multiprocessor design, we had, I think it was about 3, 4, or 5 at most. But yeah, in the 90s, it would go from 12 to 20. For example, Pentium, which was early 90s, had 5 cycles each. What a pipeline means is basically how many of those instructions I could be executing at the time. So 2 pipelines, so in other words, one optimization is to do the pipelining, and the next one is to have multiple pipelines so you can actually have multiple going at the same time. With our dryer analogy, this is easy. You have 2 sets of washing machines, 2 sets of dryers, and I guess 2 sets of hands to fold it. And so that would be 2 pipelines because you have 2 sets of everything in order to fully execute 2 instructions at the same time. Pentium 3 had 3. He puts in the word kinda because they did a couple of tricks that made it not a true pipeline. But if you really are interested, you can go into that. Pentium 4 became the 4 pipelines, 20 cycles deep. Notice it went from 5 cycles to complete instruction to 12, then 20 at the Pentium 4. And then what happened is they did keep increasing it. I think they maxed out around 35, and then they've been dialing it back because they've realized they don't need it that deeply. There are other optimizations they can take advantage of. But still nowadays, they pretty much discovered that the sweet spot's about 20 cycles deep per instructions, and we'll get a little more into that today or tomorrow about why that number exists. I did look up and find out that the Zen architecture from AMD does have 6 pipelines. The Intel is a little harder to discover. Problem is when you search for i7, There's way too many different generations. Some of them said they only had 5, some said 7, but nonetheless, they hop around 6 pipelines. Again, what does a number of pipelines mean? That's like the number of different sets of washing machines, dryers, and I guess hands to fold your laundry that exists. Alright, so if that's a little confusing, let me roll back and explain the difference. So the number of cycles deep explains how many instructions can be in flight, so how many instructions the whole pipeline can work on, and the number of pipelines is how many individual execution paths can exist. We're not going to talk more about the number of pipelines. We're going to focus on the pipelining itself, aka the number of cycles each. And so what we're going to do is we're going to break up the instruction into different cycles, similar to multi-cycle, but design a different data path stage for each one. So in other words, each path is going to be staged up. So they're going to, do we get a picture? We do not get a picture. Okay. So what we're going to talk about is what's referred to as the classic 5-stage in-order pipeline. And this was very common for MIPS and I think the 486, which was a precursor to the Pentium, and the Pentium is a precursor to the Core 2 Duo, which is a precursor to the whole i7. Excuse me. And so, stuck with this classic 5-stage pipeline, so there's going to be 5 stages that the instruction must go through in order to complete. The first one of these 5 stages is called fetch, and all this does is read the instruction from memory and then storage. You remember, hopefully previously, that memory can take a while, so spending our whole time reading from memory is very understandable. So just like before, you have your program counter, your PC, you might have an enable line to know when you're going to overwrite it, instruction memory to read from it, and then you have something that is PC +1. Notice that this +1 came back. We're no longer going to try and reuse later stages in the pipeline. By the time this in-order pipeline came about, we had a lot more area on our chips, so we didn't need to worry about trying to reuse an adder all the time. And here's the big trick with the implementing the 5-stage in-order pipeline is after a set of work is done, we're going to store the work in a register. The reason for that is this whole side is going to take one cycle, and then we want to be able to store it in our registers or our flip-flops, and then next cycle begin the next stage. So this stage simply takes the address in the program counter, goes to that address in instruction memory, and then reads the instruction so that the instruction bits are stored here. And also it stores PC +1. Why are we doing that? Well, if it's some type of jump instruction, we need to make sure we know where the address is. So we do need to store PC +1. And the rest of the pipeline is going to be down there. There is going to be a line going back to this mux. If you don't remember what this mux was for, it's if you're doing a jump, you need to be able to tell the program counter to, instead of going to PC +1, to go jump to where it needs to be. So stage 2 is to decode. So remember, the first stage is to get the instruction. This stage is going to take the instruction, figure out what bits you need to read from the register file, read those bits, and then store them out again. So read from the register file, store them in the register file, go and forward PC +1 in case there's a jump and we need to work with that, and then we just forward the instruction bits. Again, that's all we do. Notice that what we're really doing inside of these instructions is just chopping them up into the smallest parts possible. And of course, that blue line, if you don't recall, is going back to the program counter in case we need to update it. And also, you have a couple more blue lines down there in case you need to write to the register file. Notice it is telling the register file which register to write to and the data to write to it, just like in a single cycle processor. And the rest of the pipeline's on that stage. So this is the decode stage. It's in between fetch, and what comes next is EX, aka execute. Notice that these registers are labeled by what stages they're between. So IF is instruction fetch and ID is instruction decode. So this is the pipeline register between instruction fetch and instruction decode. And this is the pipeline register between instruction decode and execute. So an execute is where we do the work of the ALU, namely the add or the AND, or we test for equality, and then we forward the results along. Notice that if it's add or AND, we get the result, but if it is a memory instruction of some sort, we do have to use the ALU to compute the address, so that is going to be done here as well. So remember, we have on the left from the decode stage, We have the instruction, the contents of the two registers, and program counter +1. We may send that to the ALU and then submit the ALU result over here. Why do you have two things going to this mux? Well, remember, if we're doing a load word or store word, we might have an offset bits right here. What's not shown is the sign extend, but that's just to simplify this picture. Also, you may have to forward the contents of register B. If you are writing to memory, then you're actually writing what's from address B in there. And then we have instruction bits in case we need to also add the offset to PC +1 plus offset, because that's how we calculate our jump instruction. And of course, it's always a good idea to forward your instruction bits so you know what instruction we're executing. And that blue line going back, for those of you who forgot, is in case we have a branch and we need to update that PC +1 at the very beginning. And the lines down here are in order to update the register file. So, decode over here, execute, instruction decode, execute, execute / in between memory, because next comes the memory stage. Memory is where we actually do the load word or the store word. It's also known as move L or move S. And so we have everything from the execute stage, and hopefully and in this part we're going to either load it or store it. Alright. So first off, the ALU results is going to be forwarded along, and the reason for that is if we're doing an add or an and, we don't do anything with memory, so we're just going to take our result and forward it along. If we are doing something with memory and it requires the ALU result, which is the address, then we're going to send that and the contents of register B, because if we're trying to write to the memory, we need what data we're going to write to it. Instruction bits, of course, forward along. Notice I did skip over here. I forgot to mention that if we are reading, then it needs to give us the data that it's reading. Of course, that blue line, this goes back to the mux before the PC in stage 1 in order to update the program counter if necessary. And then these two lines are in case we need to update the register file. And so this is memory stage. So after execute, we deal with memory. And then after memory, we're going to have something called WB, which stands for write back, which is the final stage in order to write back to the register file. So design that writes it back. So if it's a load, we need to go and write the memory or the mem data to the right register. If it's an ALU result, we need to write to the destination register for an add or an and. Opcode bids control the write enable. So the memory writes. So the instruction bits are going to basically tell this mux, are we taking the ALU result or the memory read, and send it back to the register file. And then over here, these bits are wrong. In all actuality, I think in our current design, there is no need for a mux here. It just sends the correct bits back of which register it's writing to. So this slide does need a little update right there. And so our processor looks something like this. Hey, look, the sign extend got in here. So the sign extend was in decode, is where the extension was. And then it was stored inside the pipeline register. Great. Notice that we're taking each instruction and we're chopping it up into 5 different sections. 1, 2, 3, 4, 5. And so each instruction is going to take 5 steps in order to complete. But while one instruction is over here, the idea is that there could be an instruction here, here, and of course 2 instructions in front of it as well. And the idea is that these registers save off the work that has been done so far, so that the next cycle it can pick up where it left off. So, sample test question might be, which item does not need to be included in the mem write back of our, well, it should be LC32. Well, PC +1 plus offset, because by the time you get to write back, you no longer need to know where you're going, because it's in memory stage that we decide where the PC is going. Something a little more complicated. What items need to be added to one of the pipeline registers discussed in class to support sub instruction right here? That might be a harder question that might be coming up. So if you want to modify the data path, if you want to double the clock frequency, what could you do? Well, if we go back here, the idea is that instead of instruction taking this entire time to work, you've chopped it up into, hopefully, 5 different equally timed spaces. So while it takes 5 cycles in order to complete, you can increase your clock cycle count or your clock rate by a factor of 5. And since you're able to work on 5 different instructions at the same time, you can make your CPI jump back down to 1, which means you've just made your processor effectively 5 times faster. But the question is, does everything divide up correctly? Like, are these 5 equal pieces of the same instruction? Hopefully you can tell by now the answer is no. Data memory, instruction memory is probably pretty fast because we're pretty good at caching that. But data memory is probably pretty slow. The ALU, especially if you're doing multiply, it's going to be pretty slow. So you can't really chop it up. It doesn't really get chopped up, but you still get a good factor 2 or 3 speed up from this design. But the question was, could we double? If we want to double it, what do we do? Well, we find out which stage is taking the longest. Let's say, for example, it's memory, and we chop it in half. So that memory takes 2 cycles, and you put like another little pipeline right here. And so there's the first half of memory and the second half of memory. That way you can have 2 instructions inside of memory at the same time. Would that double the frequency? Probably not, because while you chop this one in half, these other ones may not, something else may become the bottleneck first, so you have to chop up other pipelines as well. And that's why if you told you in the history that processor designers were chopping up these pipelines into pretty deep, all the way up to 35 pipelines deep, I saw at some point, but we've basically settled back onto 20. We've only sticking with 5 here because of its simplicity, and it's already going to be complicated enough with these 5. So let's move on. How do you determine the frequency? You determine it by whatever the bottleneck or the slowest pipeline stage is. Alright, example code that I completely forgot to update. Actually, I got pretty close. I just didn't change the L word and the store words. Let me do that real quick. Let's go ahead and tap that out. Alright, so what we're going to do here with this piece of code is we are going to watch it flow through the pipeline. I'm going to pause recording because I spent a long time trying to fix these slides for the new processor design, but I know something's going to come up.